Can see everything okay? All right. Hello, everyone. My name is Connor Ebert. I am the team lead for UVic rocketry. And welcome to our preliminary presentation for Launch Canada 2022. So on our agenda for today, we'll go over a quick intro, give a bit of information about the team and some of the stuff we've been up to outside of our technical projects. We'll then go into an overview of Xenia-1, our 10,000-foot competition rocket, as well as our hybrid test engine, which will be our technological demonstration. And then we'll go over any questions you may have, and that'll be it. So in terms of team information, the history of UVR. So the team started out in 2015 as a capstones design project. From 2016 onward, the team attended Spaceport America Cup multiple times. Some notable mentions were in our first year in 2016. The team came third place overall out of the 40 teams attending. And in 2017, our Payload came first in the Payload competition. This year, Xenia-1 will be flying at the launch event this summer. In terms of our team structure, the team is divided up into our technical side and our administrative side, with the project manager overseeing things like business and media, with the lead engineer coordinating the subsystems and safety captain. In terms of our subsystems, the team is divided up into these 6 subsystems you can see here. Their contributions to Xenia-1 will be outlined in the presentation. For team demographics, we currently have 44 active members, which 8 of them being administrations. As you can see from our members by faculty graph, while the majority of us are in engineering, we have members from faculties from physics all the way to Greek and Roman studies, so we're a rather diverse team. In terms of going over some stuff about COVID-19 and the effect it had on us, the 2 main things that happened that were blockers for us were member loss and facility access. At its lowest point last summer, the team was down to only 8 active members, so up to 44 in the past semester was a huge win for us. However, a lot of the information was lost as our experienced members left without being able to properly onboard newer members due to the lack of access to facilities. Because during lockdown, we lost all access to manufacturing lab facilities, and with the new wave, UVic is currently back online. So our access, while we still have some access for some members, a lot of our access is a lot more limited than we might like.
All right, moving on to outreach. My name is Chris. I am the media and one of the avionics leads for rocketry. Next slide. So first thing, we went to a couple outreach events last semester, first of which was Go Eng Girl. This event was hosted by Science Venture, where we brought a couple of our new projects we're putting in our new Xenia-1 rocket, like Airbrakes, Magpie, and we brought MVB2 to kind of just give them a scale of how big our rocket was. We fielded a bunch of questions from all the young girls there, and tried to get them interested in rocketry. Next thing we did another event that was hosted by Science Venture, but this was in our rocket room on campus. We had a bunch of elementary and high school students come over, and we taught them how to make little matchstick rockets, and again, kind of taught them what it takes to make a rocket. So yeah, next slide. A big thing for us last couple semesters have been skill devs. Since we've been losing a lot of members, we've been deciding we need to still keep the skills going. So we created video series when we weren't allowed to be in person. So we made one on ANSYS and one on SolidWorks, another one on PCB design. And then once we got in person again, we did a bunch of software skill devs, a bunch of layup skill devs. We also did, I'm blanking on it right now, but we did a couple more other skill devs just on general rocket theory and stuff like that. Awesome. And also a big point last year, we got our first main event with the whole team. We did a ball drive, which was nice to get out into the community and collect some bottles. Wasn't as successful as we wanted to, but it was good to see everybody out there, yeah, and get out with the community.
So hello, my name is Adam. I'm the acting aerostructure lead for the team, and I'm going to be introducing the Xenia-1 rocket, which is this year's 10K competition rocket. It includes many exciting projects, which I'll go through right now. So the aim and purpose of Xenia-1 is to serve as a test bench for several unflown experimental projects and to gather flight data on its way up to 10,000 feet. A few exciting projects, which will be discussed in detail later, includes a completely new avionics and instrumentation package, including a black box, live strain gauge measurements, altimeters, and other comms devices, a machine-guided parafoil hidden in the nose cone, an active apogee correction device, which are the Airbrakes, a biological microfluidics experiment involving yeast and microgravity, and exterior patch antennas. And so now we're going to talk about those in detail.
Hi, my name is Arturo, and I'm the current recovery lead. Next slide, please. The recovery system in Xenia-1 features redundant systems in all of its major stages in the form of dual black powder ejection charges for nose cone separation and drogue parachute deployment, as well as a dual release mechanism or a taco link for the main parachute deployment. Xenia-1 features two parachutes, one 0.59 square meter round drogue parachute and one 15.2 square meter pull down apex main parachute. And both of these parachutes have their own sets of shock cords, nylon shock cords, which are mounted to two different eye bolts on the recovery bulkhead via swivel links to avoid tangling. And these shock cords are roughly 3 times the length of the fuselage. The planned tests for the recovery subsystem are mostly stress tests for all the major components, such as the stitching of the parachutes, the taco link or the release mechanism, and the eye bolts. But we're also testing the nylon shear screws, which will hold together the nose cone to the fuselage to verify the correct amount of shear screws that we need, and a vacuum black powder ignition test to verify the pressure that will be created inside the fuselage. In addition, we're also having a full-on avionics integration test, and lastly, a full-scale nose cone ejection test.
Hi, I'm Claire. I'm the flight dynamics lead, and I'll be discussing the flight and airframe parameters. So here are our airframe parameters. Our fins were designed primarily using RAS-Aero, pretty much running a couple different geometries and seeing what works best aerodynamically, and also keeping in mind what size the fins need to be stable. So there are 3 fins with those listed parameters. On the right there is a picture. This is a bit past preliminary design, but we have started doing simulations, and this is the result of the CFD simulation I ran. The nose cone is shown below. It's an 18-inch elliptical nose cone, and we also have a 2-inch long boat tail. Again, the nose cone and boat tail were designed in RAS-Aero. And for our propulsion system, we're using a M-class COTS solid motor from Cesaroni Technologies. It's the M2505. Specifications are listed here. The rocket is 19.2 kilograms in total, and 3.33 kilograms are just the propellant. Next slide. So for our flight simulations, our very initial estimates and trying to get a pool of suitable motors were done using OpenRocket. They just have really good comparison kind of interface to do that kind of thing. And then once we were more certain of our rocket parameters, then we continued with RAS-Aero 2 for all our other simulations. In the future, we are aiming to use ASTOS. It's traditionally what we have used for our trajectory software, but we're having some licensing and administration issues where we can't get access to that. So that will hopefully give us better simulations. And then our assumptions were just the typical launch rail conditions and the launching at Cold Lake, Alberta. And this is what we have obtained from RAS-Aero. Of course, we do have an active altitude control system, so stuff like the apogee won't be the same. Yeah, that's all I have for flight parameters.
Hey, can't quite hear the speaker there.
Sorry, is this better?
That's better.
Okay, good. My name is Isla. I'm one of the two avionics leads. You heard from my co-lead Chris earlier regarding the outreach that we've done, and I'm going to tell you a little bit more about the avionics systems on board Xenia-1. Okay, so as Adam mentioned earlier, we've done a lot of advances in our avionics system. So we have a flight computer this year based on the Raspberry Pi Zero-W. It coordinates the collection of sensor data from all of the sensors that we've placed around the rocket, storing key parameters in the black box you'll hear about in a minute from our payload subsystem, and determining what needs to be transmitted via the APRS system to the ground. So the flight computer is mostly written in Python, and we are training up a lot of members to be able to write this system right now. It is also responsible for taking information regarding our position, altitude, and flight conditions, and calculating the ideal position of our active altitude control system, the Airbrakes, using a common filter as it's a predictive algorithm. We're also using onboard environmental sensors, strain gauges, and positional sensors for all of these calculations, and attempting to store this data in our onboard black box in case of any issues. And also we have antennas that are embedded in the fuselage, so external patch antennas, because our aerostructure, the fuselage of the rocket this year is carbon fiber, which is not RF transparent, so we've had to find another means of having our antenna be able to transmit to the ground. Next slide, please. So the planned tests that we are doing with this rocket are telemetry long distance and reliability tests. So ensuring that the telemetry system we've set up can actually transmit over the 10 kilometers and ideally with an extra margin for safety, as well as ensuring that we can reliably receive these transmissions. The black powder ignition test, which we perform with the recovery subsystem to ensure that our independent altimeter systems are capable of igniting a E-match at altitude and igniting a black powder charge. The battery duration and durability tests, whose aim is to determine how long the rocket can sit on the rail before the batteries are depleted to the point that it can no longer perform the system's functions that we need once in the air. And that is all I have for you with regards to avionics.
All right. Hello, everyone. I'm Scott Peterson. I'm UVic Rocketry's payload lead this season. Xenia-1 is designed to carry 3 experimental payloads, 2 of which we're developing in conjunction with other subsystems. So in light of that, Arturo, the recovery lead who you've already met, will be introducing you to the first of the 3 payloads.
So Magpie, or Machine Guided Parafoil Mark I, is our first payload. It is currently a subset of the recovery subsystem, and it is a proof of concept active recovery system housed inside the nose cone. And it uses GPS telemetry system, steering mechanisms, and a parafoil to guide the nose cone to a programmed location on the ground. Its goal on this rocket is to test the hardware and the software in preparation for a full-scale Mark II version, which will guide the entire rocket to a designated location on the ground. Currently, the Mark I is roughly 0.3 meters long with a mass of 1.2 kilograms plus the parafoil.
So our second payload on board are the Airbrakes. A continuation of a fourth-year mechanical engineering capstone project, the Airbrakes are an active altitude control system. So this system uses a common filter to monitor and dynamically control the position of the Airbrakes during flight. This active control over the drag coefficient allows us to manipulate and control the apogee of the rocket, giving us the tools to reach our target altitudes with high precision. The assembly is located approximately mid-body, where the added drag won't have negative effects on flight path past what we expect and designed for. And the mass and size are contingent on the fuselage diameter and are shown at the bottom there. And on the right is a picture of the Airbrakes in an exploded view. And that's all for me. Thank you.
All right, and the third and final payload on board is the jam jar, which is a microfluidic biology experiment that we are currently developing in consultation with the research lab on campus at UVic. So the purpose of the experiment is to study the effects that microgravity environments have on the gene expression of yeast cultures, which will be on board. And essentially the gene expression is arrested immediately post apogee via an injection of 37% formaldehyde solution. The jam jar is located in the upper fuselage, almost directly above the air brakes, a length of 108 millimeters and a mass of 650 grams.
So for the Xenia-1 timeline, a large part of our first semester was spent onboarding and training our large influx of new members in order to mitigate the issues we'd had in the past with large amounts of information being lost. With that in mind, we were aiming to complete our design cycles by the end of February to early March, giving us approximately about 4 months to manufacture and to test the rocket in preparation for Launch Canada in August. Now, in terms of safety for Xenia-1, for the rocket-related safety hazards, with recovery using small black powder charges inside the rocket, we must safely test the mechanism and the integrity of the assembly to ensure it does not damage the rocket during flight and that it works reliably. Because composites have a complicated structure, it is challenging to accurately predetermine the strength of our layup patterns. So mechanically stress testing our composite components as well as other structural components is an integral step in the verification process. Drop, puncture, and pressure testing are some of the tests potentially incorporated into projects such as black box or other mission critical components. Hot fire testing can be very dangerous. It must be done in the correct location and with the correctly approved personnel. We aren't currently able to conduct full-scale hot fire testing on campus or locally, but when a location can be used, much preparation is required. For dealing with composites and other hazardous materials, it is inevitable when building a rocket. So the University of Victoria and the rocketry team require those handling hazardous or toxic materials to complete a workplace hazardous materials information system or WMIS training provided by the school. The hazard mitigation steps we've taken. So with so many potential hazardous tasks and experiments, we keep ourselves safe by planning all testing, not just dangerous ones, and documenting the reasons, procedure, safety requirements, and expected outcomes with evidence to support those expectations. Furthermore, all testing plans must go through the chain of command and be reviewed by team administrators before they can take place. Any additional personnel, such as the safety captain or team experts, can be involved if the test relates to them. Black powder pressure testing report should involve communication between the author, their subsystem lead, and the safety captain, for example. Now, how we ensure safe practices follows to competition. We thoroughly investigate our designs and hold multiple design reviews with many members to communicate project progress and receive suggestions and concerns from as many members as possible. Having these large team reviews also familiarizes members with the components and subsystems that their project may be interacting with. Furthermore, writing test reports and continuing to document experiments allows us to build a repository of useful information, ensuring a standard process is followed. We build a habit of double and triple checking everything inside and outside the rocket. It also builds trust between members of the team, an integral component of a safe operation.
Hello, everyone. I'm Devin. I'm the propulsion lead this season, and I will be talking about our technological demonstration, which is the hybrid propulsion project. That encompasses the Mule-1 hybrid test engine and our propulsion development platform, which will be referred to further on as the PDP. So just an overview of the Mule-1 engine. It's a nitrous oxide paraffin hybrid. And it's built inside of a Cessna Technologies 75 millimeter motor casing. It has a simple shower head injector and a composite nozzle. The following engine parameters you see below are kind of express the fact that this engine is more of a proof of concept for the team, just to show, or basically so we can prove to ourselves that we can set parameters and accomplish those with an engine that we design. And as such, it's a relatively short burn time and low thrust to reduce the potential consequences of failure during like our initial tests. Overviewing the PDP, starting with mechanical systems, we have the thrust cage on the very bottom, and that houses the motor casing and is rated for over 8 kilonewtons of thrust, and it's designed to be anchored into a concrete base. This was designed along with Mule 1 back in 2018 by a previous member, and it's completely separate from the valve carton feed system. The valve carton feed system, which you can see to the right, is supplies the nitrous oxide oxidizer and is pressure regulated by nitrogen. It has a total of 7 remote actuated valves, as well as a run tank for system isolation during firing. The electrical and software systems for the test stand start with the instrumentation. You can see the GUI on the top right there, and that's simply for data logging. And then we have the controls GUI on the bottom right, which is for the closed loop valve actuation. And it also has built-in fail-safes for connection loss, power loss, and stuck valves. The bottom image there just is a high-level diagram of how we connect the 2 mission control laptops to Raspberry Pis on the test stand. So the estimated costs for this project, the past spending, like I said, this project started back in 2018, and so past spending has been estimated around $8,500 for the construction of the engine and the test stand, and then remaining R&D considers development of a liquid level sensor for our run tank, as well as igniter and fuel grain composition changes, as well as test stand and engine testing. Remaining manufacturing budget calls for test stand upgrades and engine redesigns that were started due to feedback we received from Launch Canada's reports, or for our reports to Launch Canada last year. Okay, so our planned tests for this entire system is to start off with integration testing for the controls and instrumentation software. And once those work, having a full integration dry run of the mechanical, electrical, and software systems. Once we can ensure that the entire system operates while not under pressure, we then charge the system with CO2 and do a pressure test in terms of leak tests for the feed system, and then valve actuation tests under pressure for controls and sensing for instrumentation. And that leads into our cold flow testing to measure the mass flow, as well as the pressure drop across the system, and then the coefficient of discharge of our injector. That cold flow testing also includes emergency procedures for things like loss of signal, a stuck valve, or rapid unplanned disassembly. And that should all culminate in a eventual full system static hot fire test at Launch Canada. Okay, so this safety matrix was developed by our 2018 safety captain, and it goes over a lot of the hazards we anticipate from testing our entire system. And so we start with the explosion of the run tank, which we try and which could happen for multiple reasons. And we try to mitigate that by hydrostatically testing that vessel and then designing it to fail axially if that occurs. For a hot combustion chamber, we aim to mitigate that by monitoring the combustion chamber temperature after a successful test, or during and after a successful test, as well as team communication on when it is safe to engage with the test site again or after firing. Additionally, electrical hazards like shock or tripping are mitigated by organized wiring, communication between team members of what wires are live, as well as keeping all connections grounded. Next up, we have looking at the explosion of the combustion chamber. We aim to mitigate that we aim to mitigate that by making our initial test such small scale, only having around 4 seconds of burn time and a reduced fuel grain size. We also plan to look into either X-ray or ultrasound fuel grain analysis to look for cracks and things, as well as using a wax stabilizer during casting. As well, we also look at nitrous oxide exposure, and we mitigate that by working with an industrial gas company, Praxair, and checking all of our fittings and using oxygen-safe Teflon tape. Finally, for things like premature igniter ignition, we keep like the leads shorted during handling and up until the test site has been vacated by the team, or up until the team is ready to vacate the test site. An industrial tank explosion due to backflow is highly unlikely due to isolating it with a run tank. Nozzle ejection is a known failure for other hybrids, and so no member is allowed in the blast zone once the system is charged, and we also anticipate having we'll need a backstop in the event that a nozzle is ejected. And finally, a loss of communications will be mitigated by fail-safes designed into our control software. That kind of leads us into safety requirements from Launch Canada. And so not too many, just a concrete platform for thrust cage mounting, a downrange backstop in case of nozzle ejection, a minimum 150-foot radius around the site in case of rapid unplanned disassembly, and clear sight lines to the test site for wireless communications. This is the timeline for Mule 1. This is the timeline for Mule 1, and this starts with, last semester, as Connor kind of mentioned, the first semester back in person was a lot of project assessment, as well as new member orientation. And so right now we're finishing up the combustion chamber redesign based on the report feedback, and moving into manufacturing for that at the end of the month. We have actually organized a potential hot fire test with UBC, because as you may know, we do not have, or here in Victoria, we don't have any testing locations. However, they've offered to let us use their test stand, which is very nice of them. And so that would allow us to kind of better anticipate the performance of our engine come Launch Canada. And so while that's happening, our controls, instrumentation, and valve carton feed system team are working to have our own test stand ready for competition. And that leads into integration testing up into cold flow prep. Oh, Connor, we're not done. Up into cold flow prep and then the cold flow test right in the middle of finals, given a break for finals. We'll then do any iteration or optimization that we need to up until assembly rehearsals and preparation for Launch Canada. Just reading I got a comment, examples of what you consider high consequence events. That's a good question. In terms of, I think the safety captain from 2018 downplayed the personal injury. I think, at least in my opinion, I think personal injury is a pretty high consequence, and should never be in this be associated with the same hazard that has more than a low risk of occurring. But off the top of my head now, I can't state any other high consequences. But other than that, I believe that concludes our presentation.
All right. Well, thanks a lot, guys. That was a good presentation, right on time. So appreciate that. first of all, it's really good to see how you've been managing to move forward in spite of the challenges. I know it's been difficult for everybody, and you certainly highlighted the knowledge retention issues and loss of people and such. But it's great seeing some of the initiatives that you've been using to try to address that. Love the skill devs. That's a great idea. Good look at the team and the demographics. That was really nice to see. I think that in terms of the overall organization of your presentation, and I've said this to other teams as well, try to start high level and give people a good look at the overall project before you start diving into the detailed subsystems. So, for example, you gave us a little bit of a look at the rocket, but it would have been nice to see a little bit more covered there. Some of the way you'd structured the sections seem to be jumping around a little bit as well. So if you follow that kind of top-down approach, it's good to start with the overview. Then you can look at the mission level stuff. So things like your flight simulation, that would be mission level. Looking at mass budgets for the rocket, that's all like the top level stuff. And then from there, you break it down more. Otherwise, it can be sometimes a little bit hard to follow if you're jumping around a lot. So just a thought there. Recovery system, you're obviously doing some really good CAD work. It would have been nice to see a little bit more detail on some of the critical areas, though. So the recovery system has some of the highest stressed areas in the entire vehicle. So focusing in on some of those areas would have been useful. Also, you talk about the release mechanism, but you didn't really show it in any detail. So that's the kind of thing that we would like to see a little bit more of, I think. Testing, and this is something that comes up a lot as well. Try to tell us more about the details. And you were a little bit better in the propulsion section at that than some of the other places. But in general, when you're talking about doing a test, try to be as specific as possible about what exactly the test conditions are and what it is you're trying to measure from it, and wherever possible, use numbers. So, for example, you talk about testing for long distance and reliability of your telemetry. What does that mean? Put numbers associated with those. So, tell us what distance is your actual requirement. What level of reliability is your requirement? So be as specific as you can. Similarly, when you talk about testing for battery durability, that's going to depend on a lot of things. It's going to depend on the current draw the battery is providing. It's going to depend on the temperature as well. So what are the conditions that you're actually going to test for? Maybe you're doing a range. That would be what you would normally do in industry, but you'll want to try to be specific about that. Otherwise, it's hard to know what to make of test results like that, right? One thing I really love is the various payloads and technologies that you're trying to incorporate. I think there's some really cool stuff there. And I like that a lot of these things are more or less standalone projects as well. So that's kind of neat. The parasail is very cool. Yeah, a lot of good stuff there. Looking forward to seeing that come together. It would be good to see a little bit more discussion on what you're doing on the vehicle side of things to try to accommodate all of these payloads and things that you're building into it. Have you allocated a certain amount of mass for these things? Have you incorporated other features into the design of the overall vehicle in order to accommodate these things? So this is where taking that kind of systems engineering approach can be very helpful, because it shows how you come up with these big high-level requirements and then how those translate into the design of the individual subsystems and components. So the more you can kind of approach it that way, the better it's going to be to convey what it is you're doing to everybody. For the hybrid, I will definitely echo Adamir's comments. The way you presented the hazard analysis was really good. That's exactly what we like to see. But yeah, you had a few very questionable characterizations there. So the consequence of a tank explosion was described as third-degree burns or fatal injuries, and that was called a medium consequence. Fatalities are not a medium consequence. They are the highest possible consequence. So the approach is good, but please go back through that and revisit any sort of remotely serious injury is probably going to be a medium consequence at least. And if it's fatal, then that is the top. So like Adamir said, if a fatality is a medium consequence, then what on earth is a high consequence? So yeah, please do revisit that. Those I think are the major things that jumped out at me. But yeah, good job, and I'm really looking forward to seeing all of this come together. Other comments from judges?
I can go next.
Go for
Very
it.
good presentation. Again, I'm aligned with most of Adam's comments. The flow should reflect the flow of your thought processes in the structured engineering design process that you're following, from the mission to the overall rocket requirements to the requirements for each system, and then how you've made trade-offs in that context. You know, you showed us a lot of what you chose, but why you felt this was the best decision and how it supports the overall mission. You know, we didn't get to see that, and to some extent, that's the most important thing, is to show you're learning how to do this engineering process, because wherever you go in your career, that's exactly what you'll be doing. I really liked the safety matrix. I'm in the system safety team here. So what we do is we start from the hazards. So again, things blowing up or catching fire or failing to work, you know, and then for each one, we try to assign a level of hazard. In aerospace, it would be minor, major, hazardous, or catastrophic. And then we ascribe a maximum probability that it's allowed to have. And then, so when you say, well, I have a valve that'll prevent that from happening, you say, well, what's the probability of a valve failing? Maybe we need to have a redundant system. And how sure am I that all my backups are redundant if they're all fed from the same electrical system, for example, and that goes out, it might take them all out at the same time. So kind of a structured fault tree working downwards from the top hazards down to what can contribute to them. And that works down to the components, and from the failure modes and effects analysis, you're working up from the components, and those should meet in the middle. And then you would have a very structured way to show what are all the possible hazards, what does your system need to do, malfunction or bad inputs or what have you, for that to happen, and what's the probability, and can you mitigate it? And then it becomes very open and transparent, and people can review it and confirm it's acceptable. So that's kind of, it was a real step in the right direction by the students who did it. So I encourage Devin and Connor and the team to, you know, kind of think about that and say, you know, how would we do that for the whole rocket system? You know, even if it's not fatalities, other malfunctions that result in loss of the mission, we would give that some level of hazard as well. That was about it for me. Thanks very much. I enjoyed it, and good luck to the team.
Thanks, Avram. All right, who's next?
I'll say one more thing. There's just this one more thought that I wanted to add to the comment earlier. Devin, when you were explaining, you know, or you were giving the response to my question, it sounded like you were kind of saying, well, this is work that was done previously, and so we're just incorporating this again. That's kind of how it sounded to me. Remember that this is like, this ends up being your like your team's rocket. This is the face that you're presenting to us. It can't be someone else's fault. It's, I mean, like, and I guess like just be careful about like assigning work or ascribing work to previous team members and not doing the update to it, because the update falls to you at the end of the day, and you being the collective team, not you, Devin. So just keep that in mind when, you know, for next time you're answering a question like that.
Yeah. Okay. Thank you.
And this is something that comes up a lot, frankly, with student teams, because you naturally will end up inheriting a lot of things from the previous incarnation of your team. And when that's happening, it's very easy for things to kind of get lost in the mists of time. But it's important to not just blindly inherit what was passed on to you without understanding the bigger context around it and being critical of it. Otherwise, you might find that you get, you know, on one level, you know, potentially awkward questions and presentations, but potentially, you know, it can lead to failures or other actual technical or safety related problems. So just do bear that in mind.
Yes. Okay. Thank you. Yeah.
As Paul says, own it and understand it. That's
yes.
That's a good way of putting it.
Got it. Thank you so much.
No
Yeah.
problem.
I can understand that. The pushing the blame aside, it speaks more to complacence rather than lack of ownership. I mean, it's the one thing that we have struggled with the team this semester has been like lack of safety captain and project manager, which we're working on. And so that will be a large part of a safety captain being enacted. We'll be revising, especially the hybrid safety matrices.
Yep, that's good. All right. Judges, who wants to go next?
I'll go.
All right, Chris.
I don't really have a whole lot to say because you guys did a really good job, and everybody else has sort of touched on the bigger things. You will immediately get on the judge's good side when you start with an overview, and the very next thing you say is recovery. That is almost never done. Almost never. The fact that you guys have started with recovery and then talked about how you're going to have a successful mission in terms of a team mindset, that is exactly what we want to see. To start with that form of thinking of recovery first. Again, based on, I won't touch on what other people have already touched on. So you have a carbon rocket, and you have antennas on the outside of it. So are you doing a phased array, or what are you doing to prevent a lost rocket?
So what we are doing is we have a carbon fiber rocket, and then our goal is going to be to embed antennas between that and a fiberglass exterior to ensure it does not have any impact on the aerodynamics. And at the moment, we are planning to have one antenna on the outside. However, it has been a point of consideration whether we should have three in some sort of a phased array to ensure that we always have that line of sight communication with it. It's right now a matter of figuring out exactly how many we would need in order to not lose communication ever. And that's something we're currently looking into quite a bit.
I can say from, well, I was thinking about doing something similar, and ultimately I chose to have a fiberglass section of my rocket, specifically a fiberglass nose. The value of the weight savings of carbon in the nose, I mean, naturally you want to bring your CG high. So the weight, the additional weight of a glass nose fixes the RF problem and just means you don't need any of the phased arrays. If you only have one antenna on one side and it rolls away or it lands and that thing is on the ground, good luck finding it. You better have seen it on the way down, because or hope for blind luck, because you won't find it. You're off.
Yeah. So this is something that we were considering when we initially designed this rocket. Normally, we would have a fiberglass coupler in the middle or a fiberglass nose cone. However, due to the number of systems we're testing on Xenia-1, the nose cone has to be allocated to Magpie, as it is a separate component that detaches in order to just test that system without having the entire rocket on it. And the coupler is dedicated to our active altitude control system, the Airbrakes. And so we found that there was no way that we could have a fiberglass section of the rocket for the antenna, but normally we would put it in a fiberglass coupler or a fiberglass nose cone. This is the first year when both of those positions have been taken up by other projects. So we are experimenting with external antennas.
Well, what I would recommend as you go, if you are going to have a single antenna or you are going to have a phased array, build what you're planning on doing, and then take your rocket for a walk. Like literally, go to a park and go for a walk. And when you lose sight of your rocket, you'll know exactly whether, or even, you don't even need to complete the entire rocket. Just make your fuselage, right? Don't attach your fins, minimize your work. Just make a carbon tube, throw your antennas on, glass them in, and then go for a walk with it and see if you can find it. And if you can't, you know that you need to reinvent, or go back to the drawing board. So when I heard carbon and antenna on the outside, I immediately went, uh-oh, they're not going to find that thing on the ground.
Okay, thank you. That has been something that we've been spending a few months trying to establish. So that's a test that I'll be sure to add to our list.
Excellent. How fast do you plan on going?
It's just a little above Mach, like it's maybe Mach 1.1.
Okay. Because your choice of nose cone sort of surprised me. Normally, teams don't go with an elliptical. Normally, they go with a hack or a VK. So I just was surprised when I saw that shape. But I mean, that's again, this is nitpicking at this point. You said that you used Open Rocket for everything up to when it leaves the launch rail, and then RasAero for anything above that. I'm just curious, do you run the full simulation in Open Rocket and cross your stability over motor burn? Because that's one of the things that Open Rocket does really, really well. I use Open Rocket almost exclusively. I do the whole flight in Open Rocket and then go to RasAero just to validate my results. I'm just wondering why you chose to use Open Rocket only until it leaves the launch rail.
Sorry, what I meant is for our early on simulations when we weren't sure which motor we were choosing, we used RasAero or Open Rocket for a full simulation, and then once we had a good idea, because it's a little annoying, I'm sure you know, in RasAero to like compare stuff. So once we had a good idea of what size motor we were using, then we continued doing the full simulation in RasAero. And because of the speed, we didn't bother with Open Rocket anymore because it starts to be inaccurate about the transonic sonic range.
I have had no problems with Open Rocket, and even Mach 1.8, 1.9. Open Rocket is just fine with transonic and super. But I know other people don't think that. I brought this up with Adam at the beginning of the recovery section with respect to the guided recovery. I guess it was 4 or 5 years ago, I was told that guided recovery would be considered a guided well, there are just rules with respect to it. So I would just, and maybe Adam and I can do some homework with respect to that. I'll find out
Yeah.
where it is that I saw that. I was told that sort of guidance is fine for gliders. It's fine for rocket planes. It's fine for RF. It's fine for that, but it's not fine for rocket recovery. And it didn't make sense to me at the time. It still doesn't make sense to me. But I just remember that I was told that you can't do that. So it's just, don't stop your work. Let's just make sure that you get to the US and nobody says, what the hell are you doing?
If I can interject here,
Please do.
I was looking at the regulations for the US specifically, as sometimes they're a bit more strict than Canada. And I did see that it was not permitted for rocket recovery. It seemed to indicate, though, that it didn't specify rocket components. It said rocket. So the thought was, well, it didn't say rocket, but it implied rocket as we would know it. It seemed to say that just the nose cone would be okay, but also because it's not under its own propulsion, it seemed as though it might not concern anything. Most of the design and development was done by team members several years ago, but we have looked into whether or not it is acceptable, and I haven't found anything that said that it wasn't so far. So if you have something that gives a reason why it's not allowed, I would love to see that and make sure that what we're doing is all right. This is something where I did look at the rules and I read through that section of ITAR and tried to figure out if it fit, and I didn't see it. So
okay, we can take this one off line in the interest of time, just to keep this moving along. But yeah, we'll take a look at that. David, do you have anything you wanted to add?
Yeah, I just kind of following up a little bit what Chris says. You had mentioned patch antennas on the rocket. What frequencies are you running?
our goal is to work on the 2-meter band.
You're not going to go for a patch antenna at 2 meters. That's a fairly big antenna. Carbon acts as a conductor, so if you're embedding antennas in the carbon airframe, the carbon acts as a ground plane. Your total impedance mismatch is going to happen big time. So I think you really need to rethink that. Going to higher frequencies might be a better one than 2-meter band. I'm assuming somebody must be an amateur radio or have their ham license.
I have my amateur radio license.
Excellent, excellent.
This is something I hadn't figured that bit out yet. I knew that we would need to isolate it and make sure that it wasn't grounded. I hadn't realized that it would potentially have that big of an impact.
You'll still get a transmission, but if you want some more information, you can maybe get some contact and can help you out a little bit with that. The risk matrix seemed to only apply to the hybrid motor. You probably need a risk matrix for the rocket itself. Curious at why you're using N2 as a pressure for N2O for nitrous oxide.
I actually that's a great question as well. The system was designed doing the same thing here, I understand, but the system was designed before I took over the project. However, I'd be willing to hear arguments against that. The biggest thing I believe was actually, no, I don't actually know why N2 specifically.
I can take that one because I think I was the one who recommended doing that. And just the history lesson there is that nitrous oxide, the vapor phase of it, is very prone to decomposing. And so the greatest danger of that happening tends to be at the end of a burn when you've got your tank filled with vapor and hot injector downstream of it. things have been known to pop. And so diluting the nitrous vapor with an inert pressurant goes a very long way to mitigating that. Now, for a rocket that you're flying, that's not always practical to try to add in a whole other pressurant system. But for a static firing, it's not all that difficult to do, and it actually has a big safety benefit.
Okay, thanks, Adam.
Yeah,
No
thanks,
problem.
Adam.
But the just kind of finishing off from my side, the great presentation. I think you covered a lot of the basis on there. A little bit light on the flight profile piece of that. It seems that you have two streams and you tried to pack it all into one presentation here. So.
Yep, we'll look forward to seeing some of that fleshed out a little bit more in the report. So especially the comments related to how you structure things, do bear those in mind when you're putting the design report together. Okay, we've got like time for 60 seconds worth of questions. If anybody has one last word they want to throw in.
I love the power foil. I think that is way cool. I want to see that developed. Please go.
Yeah, a lot of thumbs up there. And I could have sworn that we've had that at the Spaceport America Cup as well. I'm going to look into that. ITAR is admittedly weird, and so something being restricted doesn't have to actually make sense. It might still be, but yeah, we'll look into it because that's super cool, and I think we all want to see that.
But if the thing stays tethered to your rocket and it's just you're testing the telemetry and the commands and all that, like, you could still do a pretty good experiment where you show, if it hadn't been connected to the rocket, it was sending all the right commands to send it flying in the right direction. So it might be.
Yeah, that is a good alternative. We will consider that. Thank you.
Mm-hmm.
All right, well, if there's nothing else, we can wrap it up here. Thanks a lot, guys. Once again, great presentation. Keep up the good work. Looking forward to your report, and reach out anytime.
Yeah, just on behalf of UVR, thanks a lot for all your awesome feedback. Got a huge page of notes here to go through now. So really, this is a great learning experience for all of us, and really appreciate it. Thank you.
Our pleasure. We'll make the video available for you guys as well, too.
Thank you.
Great.
All
Thank
right.
you so much.
Take care, guys.
Thank you.